So hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal pump, including solid parts and also secondary flow path from scratch in CFturbo software, and then how to simulate it and evaluate it in TCFD software. The webinar is being recorded, and its recording will be made available on our YouTube channel. Just fine. In case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. Please let me start with introducing the speakers of today's webinar. So this is me. My name is Luboš Pirkl. I am co-founder of CFD Support, and my current position at CFD Support is telling the world what we do, and I'm gonna guide you through today's webinar. I am here in our Prague office with my colleague Radek Máca. Hello, Radek.
Hello, Luboš, and hello, everybody. And also in advance, hello, Oliver, to Dresden.
Hello, Radek.
Okay, so I will only notice that Radek is our head engineer and senior developer here at CFD Support. And finally, together with us on the line, there is Oliver Felde from CFturbo in Dresden. Hello, Oliver.
Hello, Luboš, and hello, everybody out there.
Yes, so Oliver, are you ready for the webinar?
I am ready, yes, and I'm looking forward to participating in it.
Okay, so that's perfect. So I only note that Oliver is Senior Manager CAE at CFturbo company. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms in CFturbo software. So this is us. About the agenda of today's webinar, there will be 4 parts. In the first part, it will be this general introduction. In the second part, let's call it the design part, there will be a live example where Oliver is going to introduce CFturbo a little bit, and then he will show us a live example of centrifugal pump with including the solid parts and also the secondary flow path. He will design this or show this pump how it's being designed from scratch in CFturbo, and then after that he will export the designed model to TCFD. In the next part, we can call it the simulation part, there will be other live example where Radek is going to show you the TCFD simulation of that centrifugal pump exported by Oliver from the previous section. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask the questions. There is a special window below, so all the questions will be answered. Some of them will be answered right in the webinar. The rest will be answered later via email. So feel free to ask the questions. It's your time. Just get involved, take the opportunity, and we will gladly answer all your questions. So this is the agenda, and I think we can move to the design part of CFturbo. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Thank you, Luboš. Well, CFturbo is a German-based company with office in Dresden and at Munich, and since last year also an office in New York City. Our main product is CFturbo, which we call a conceptual design tool for turbomachinery design. It's a modern, powerful, and user-friendly software tool. We have implemented latest design theory. Right now we have something like 200 active clients globally, and there are a couple of modules implemented that one can use to design pumps, compressors, fans, blowers, and turbines, plus some additional components like vaned or vaneless stators and diffusers and volutes, of course. And we serve with that software industries like aerospace, automotive, consumer products, mechanical process engineering, and semiconductor. I would say that's the main industry we focus on.
Okay, thanks. So I think you can take the presentation now.
Okay, you should now be able to see the central entry into CFturbo, our gray desk. I'm not going to design completely from scratch this example I want to show in the live demo, because that would cost a bit too much time. But you can look at our previous webinars where we designed this NQ49 radial pump and where Radek ran the simulation on it. So this is the model I'm going to take as a starting point, and that's why I just open it rather than really design it from scratch. And what we did in that former webinar was just to design the flow path, which means all the surfaces, well, most of the surfaces that are in touch with the fluid, and of course those surfaces of blades and so on, which really matters if it comes to the hydraulic design. So this is my starting point from today, and in 3D it would look like that. The central design step I'm going to use today is what we call the meridional contour design step. This is, as I said before, the representation of the contour that is in contact with the fluid or with the water in this case. In the first part of the live demo, I'm going to add material solids to hub and shroud. And then to this end, I just change the tab to the second one and initially tell the program to add some sort of a contour to hub and shroud. And this is given here. And the basic operation concept is that there is a lot of functionality put into a context menu. The contour can be represented either by a line segment curve or a set of line segments curves or of a set of Bezier curves with variable control points. So the shroud, for instance, is just one Bezier curve with a couple of control points. And I just want to show what one can do now in order to, for instance, get a nice kind of labyrinth ceiling here at the inlet of the impeller, and how one can use the context menu to this end. That's why I'm going to right click on the curve and say I want to make a split at this position here. And very often this first part of the shroud is somehow shaped in an axial way in order to fit to a casing that also might be axial. And that's why I'm going to get rid of those polygon points, and I'm converting this first curve, which is a Bezier curve, in a line segment curve. And here I don't need this inner polygonal point anymore. And if I zoom in a bit, I see that that is not parallel to the axis. So I can just grab that last point, and because there's also a snapping implemented, now I have a perfect coaxial inlet contour of the shroud. On the other hand, I also can right click at this polygonal point and can directly set the radius and the actual position I can also add a certain radius at this point. Okay, so that's for the time being the contour of the shroud. More interesting is probably to design the hub in a way that there might be an axis coming in and there might be a hole probably designed in order to just be part of the connection between impeller and axis. And to this end, again, I move those control points to a certain position, which again can be set directly by entering, for instance, the actual position, and by also enter the radius of the hole, which might be, for instance, 10 millimeter. What I want to do now is, again, split the curve here, make that hole, convert the Bezier curve into a line segment, convert it here into a line segment, and merge the curve in a way that there are only two parts of the line segment and one inner control point. And if I do so, and if I click OK, I have in 3D my first initial design of, if I run quickly, a model finishing, including some fillet creation at hub and shroud. And by doing so, I have my first initial shape of the material solid of the impeller, and that would just look like that. But of course, I want to do some more details on the hub, and that's why I'm going back to the meridional contour design step, not this one, and carry on with designing this little back shape of the hub. Again, I make a split here. I do another split right here, just in order to make it a bit thinner and save some material. Convert this into a line segment. This two, merge those two segments and apply a radius, which might be, for instance, 4 millimeter at this point. And maybe I need some more structured work here in order to make it stiffer or so. That's why I just quickly want to show how that could be done. Another split that can be moved like that. That can be a line segment curve. There might be a split here. No, that was wrong. A split here. And line segment, merge, radius. And as easy as this contour has been done. Split it again here, split it here, move it there, make it to line segment, merge those line segments, split. That was too much. I'm using the undo feature, and the control point is gone again. So what I want to do here is make it line segment. This is already one. Merge this again and apply a radius. Yes, and here we are very quickly. Maybe that could be a bit wider. Okay, anyway, that's going to be the one that should do it for the time being. Again, if I go back to the 3D model, run the model finishing, then I have my material domain, the solid of the material domain. And because one parameter prior I start with the design is the density of that material, because of that, I can also tell what are the geometric information on that solid. And here it shows that because we have the volume, we can also calculate the mass, that is 6.5 kilogram at this point. But maybe more interesting is the center of gravity and also the moments of inertia, because that might matter in the final construction. So this was part one, just the generation of the material solid. And now I want to add the contour of the casing in order to create this what we call the secondary flow path, because that's especially with shrouded pumps very important, because there might be always some sort of a leakage flow that flows backwards, and that of course will decrease the volumetric and therefore the overall efficiency of the machine. Okay, to this end, I enter again the meridional design step, but now go to the very last tab and check this activate secondary flow path design, and it tells me there must be always a gap between a stator and a rotating component, because otherwise there wouldn't be room for the fluid to flow back. And that's why I go back to that first stator here, just have a little offset at the outlet. Now you see here the gap. Just want to move that to the correct position. And now I have between two adjacent components always a gap, which is necessary in order to really create this secondary flow path. And if I now go again back and activate that solution, I get this initial if you want geometry or guess of the geometry of the casing. And now the operation is almost the same as at the hub shroud solid generation. I can grab control points, can move them, can insert new Bezier points, can make a split, which I'm going to do at this point. Carry on with making splits. I just want to keep the secondary flow path not too big. That's why I move it a bit closer to the material domain. Split it again. Make it to line segment, merge it. Make a split. Line segment, make another split. And apply a radius again. Split it again. Control Z, that was too much. We'll make it to line segment. This is already line segment. Merge the two line segments, and now I can apply another radius. Okay, and yeah, maybe I can show you how the Bezier functionality would work. It would be like that, and so I can also reach some tangential transition between adjacent components. So that would be maybe at the inlet, at the shroud, and maybe I can, no, not a, busy, split it again here and do something like that. And do the same here at the other side, make a split, move that control point to the inner part. And because I want to have a kind of ceiling here, I want to move that casing very close to the shroud. This can be done like that. Split it here, split it there, make it, well, that's not really necessary, but I do it just for completeness. And here I want to get closer to that contour defined by the hub, and that's why I'm going to increase the number of Bezier point. And yeah, I have all the freedom here and can add as many as I want to, but I don't waste too much time of it. So maybe that might do it. If I'm going to put, if I make a fit view, then I have now the following meridional contour of the complete stage. And you see here that there is solid part, and that is covered by the inner part of the casing here. And if I go back again to the 3D model, I can run a model finishing, which takes a couple of seconds. And once that is ready, not only the material solid is generated, but also the fluid solid. And all the surfaces that covered this fluid solid, which is displayed now here. And if I make a clipping through that, you can see how the secondary flow path is now generated. As I said earlier, depending on the pressure difference that is generated by the pump, there might be some backflow, and of course then the inner part of the impeller will see more fluid flow going through that and will therefore decrease the performance because of the lower volumetric efficiency. And on the other side, at the shroud, there is some kind of empty room where one have a rotating wall close to a stationary wall, and of course there will also some losses generated in that. Okay, so my final step now is to again export everything to TCFD, because that's the simulation package that is going to be used for the simulation or the validation of the design. I just have to define a unique name for it, and also the export destination. I can set some parameters, and in order to save some time, I make the triangulation a bit coarse. And then I can start the export, and the first file that is exported is the TCFD file, which is the control file and holds all the information for setting up the CFD in TCFD. And all the next data that is exported are STL data that describe all the necessary surfaces that cover the fluid room. Yeah, and because it was quite a coarse STL triangulation, it's quickly ready. And I'm now ready to pass the presenter mode to Radek or to Lubos. Thank you.
Okay, thank you, Oliver, for the turbo machinery design part. And now we move the simulation we move in the webinar a little bit farther. So I'll take back my presentation. So yeah, so this was the design in CFturbo. Yeah, and before we move to the simulation, I would like to show you, I would like to give a brief description what is TCFD. So TCFD is a unique software developed by Czech company CFD Support. It's a smart, easy to use and affordable CFD software. TCFD was designed for CFD simulations of all rotating machinery such as fans, pumps, compressors, turbines, turbochargers, hydro turbines, etc. Both radial and axial machines, both compressible and incompressible fluid flows. TCFD numerical solver is based on OpenFOAM, and we believe that TCFD is unique at least for 4 reasons. So number one would be TCFD is perpetual, and also it's unlimited for any number of users, jobs, or cores. It's also automated and focused to individual workflow to maximize the value getting out of it. We deliver really good technical support, and also the real tutorials are included, so the user has no doubts about the best practice settings, and the start of using TCFD is very smooth for this. There are many other benefits of using TCFD. I'm not going to go for all of them. I finish here with my last point, that TCFD is developed in a way to support the value-added activities of its users. The beauty of TCFD is that it's the user who decides how deep to dive into CFD or not at all. And all the options remain open at the same time. So it was really quick introduction to TCFD, and now it's time to show you how it works. So Radek, are you ready for your part?
Yeah, hello again. Yes, I'm ready. So can you give me the presentation? Okay.
Yes, here you go.
Thank you. Okay, so let's start with the practical part of today's webinar. So I will directly use the export from CFturbo. So basically here we have the STL files which define our geometry and the TCFD file. So I will immediately open it. Now, because I have two installation of TCFD, so now I'm using the brand new TCFD, which was released recently. So I will really do the workflow in the brand new version of TCFD. So now everything is loaded. Well, I am always impressed how quickly can Oliver design any turbo machinery design from really the scratch, even with included this leakage parts. And what is mostly important, that the CAD geometry or the export is directly ready to use for CFD purposes, which is usually a bottleneck. As you I think every of CFD engineers sometimes face this problem, that how quickly get the CAD data ready for the CFD computation. Yeah? So usually it is a bottleneck, but if you use CFturbo, you will get the CAD data, or basically the geometry data, ready for CFD simulation. Okay, so this is our design, and now what you see is the graphical user interface for TCFD. So basically the layout is as follows. Here is some pipeline browser in which we can add any layer of ParaView, some default layers, or any layer which we have implemented. Here is the setup part of the CFD simulation, and here we have the render view with in which we can visualize the input geometry, created mesh or imported mesh, and final results, together with some output messages during the simulation or during the whole workflow. So just because I would like also to compare this geometry with the leakage to the old one from previous webinars without the leakage. So just to see the difference, I will make just a cut to see the meridional contour of our geometry. So I will just choose one contour. Okay, so just for nicer visualization, I make it more visible. Okay, so as you can see, you can really play around with the visualization to really make cool pictures to present. And for example, I will hide a little bit the volute. All right, so this is our contour. As you can see, there are 3 colors. It's because that the whole geometry consists of 3 parts. We call it components, which helps to set up the CFD simulation, because you need one part which is rotating and other stator part which is non-rotating, and there must be special treatment at these interfaces how to get information from the rotating component to the stator one. Yeah, so this is today's case. And just to compare to the previous one, I have already loaded, which is, I think, here. Yeah, so this is really the geometry from the previous webinars, just with the flow part, no solids and no leakage parts. Yeah, so at the end, we will shortly compare the results to see the performance of the simulation without the leakage and with the leakage. So go back here. So the setup of the simulation, so I will go back here for the setup part. The setup is very similar, almost the same, with the same condition as the pump from previous webinars. What is new in this new version is that there is an advanced button under which you will see more options to be set. And for example, for basic use, there is no need to enable the advanced setup. So this is more clear. This is really the most important and some of them compulsory parameters to be filled before you can run the CFD simulation. But anyway, using the CFturbo export, you will get these values preset. So there is no need to change almost anything. Just if you want to simulate wider range of flow rates, so you need to set it here. So let's go for that. For example, I will just show you this general menu shows us what the CFD file is loaded. We can use this check setup button to see if our setup is okay, machine time, of course, machine type, and other. Inside the simulation, important part is how many processor I will be using for the simulation. So my laptop now has, I think, just 4 cores, so I will change it to 4 cores. Anyway, I'm not gonna simulate this live, because of course the pump with the leakage needs to have more cells inside the computational mesh to really resolve the leakages. So there is no time within this webinar to see the results. Anyway, for example, I can show you the difference between the advanced and standard setup. So inside the advanced, you can see that one item is added, which is the solver steady state. So for very advanced users, they can create your own solver and implement or run it directly here. So just an example of advanced menu. Well, all the other parts are the same. So physics, water, and some parameters of the water. Inside the components, so from CFturbo we get almost the same, let's say, or very similar, at least very similar geometries. Only we have some in addition, such as these solid walls defining the leakage parts, both at the shroud side and hub side. So this is only one difference between these two cases, and of course we need finer mesh here to really have a nice and fine mesh in the leakages. As you can see, if you compare to the previous webinar, the setup is very the same, and yeah, I think there is nothing to be said more than in the previous webinars. So the speed lines, again, we are simulating just one rotation speed, of course, with many points, so with many different conditions. Again, so we simulate the pump under different condition in sense of the volumetric flow rate, usually from the highest flow rate to the lowest, just to really reveal the full performance map of this pump. Boundary condition at the outlet, of course, there is zero static pressure. Initial condition, so some reasonable gas, which is already preset, some advanced simulation controls, and as usual, post-processing tools, just such as averaging window. My favorite units to be visualized at in the final report, from which part I would like to, or I need to evaluate the efficiencies. For example, some of you needs just the efficiency of the rotor wheel separately, and then of the full geometry or without the inlet pipe, for example, or just the efficiency of the volute. So everything is possible. It can be set here, and some standard automatical post-processing visualization which can be defined here. Okay, so at the end we are fine with the setup. We can move to the TCFD manager, which is here. So again, we can click on it, activate the filter. What is new here is that there is a live residual visualization. I will show you in few seconds. So then how it works, then I can set write the case, so it creates all the necessary files and the directory structure. And after that, as usual, we can run all at once. So now it is creating all the necessary stuff, checking the input geometry and so on. And finally, when the case is written, we can click run all, and now the meshing part is done, and after that there will be the simulation itself, and at the end an automatical post-processing will be done. Just to show you how the residuals are visualized, I have somewhere here some really simple case which runs very quickly. So now when I start running calculation, you will see directly here in this window the residuals of your simulation. So you can see live if your simulation converge as usual or converge well, or if there are some problems, to go back and check for example the setup, the CFD setup, if I don't know if I set the initial condition properly, if my mesh is okay, and so on. So you can really get the information, graphical information during the simulation. Okay, so of course you can always modify the layout to be nice for you. So this was the example of the residual, which is a new feature for the current and the newest TCFD 18.06. Okay, so at the end, because my simulation will take more time than we have, so I'll where is it? So now I think, yeah, it's still meshing. Okay, now the pipe is already meshed, so anytime we can visualize the mesh. So just I can click here, show, I will hide these components and this slice. Yeah, and this is my inlet pipe mesh, right? So anytime I can see the quality of the mesh. Okay, and at the end of the simulation, so I will jump in time, and I have prepared it somewhere. where is it? Oh yeah, here of course. So at the end of the simulation, you will see here 3 dones, and then the report will appear automatically. So the report is really nice feature because there is no need to spend time to get some manual post-processing. You will get everything at one place, nicely presented. So basically the simulation statistic as usual, and for example we can stay for a while at the head visualization. So this is the graph for each point we have simulated. So graph of the head with respect to the flow rate, or also the tabulated values for some presenting usage, let's say, or comparison usage, to see convergence of the head, to see if it is okay and well converged, and the same, for example, for the efficiency and other parameters which already we have talked about the last webinar. So the usual HTML report you can have. And what is another nice feature which I would like to show you is that you can compare two reports. So it is really useful if you simulate more simulation with different geometries, mainly for example for some optimization purposes or from any other purpose. So for example, here I have the computed case with the pump with leakage, which Oliver has generated, and the old one, the pump with leakage CFturbo with no leakage. Basically, the 2 examples I have shown you. So this one and this with the leakage. So I can create, for example, the folder for compare. So compare simulation, for example, compare simulations, and here I will generate the reports which contains both reports from my simulation. So I can, for example, open the new TCFD, so new ParaView graphical user interface. Then there is a filter which is called compare reports, I think. Okay, maybe I will stop the simulation. Okay, now it is already loaded. So now I don't need to load the new case, but I just need to go for the sources menu, and here is the TCFD. Oh, TCFD compare, not report compare, so TCFD compare. So here's the output path. So I will find my compare simulations directory, which I have just recently created. Okay, and I add the HTML reports of my simulation. So I have to go here. So these are my simulations. So first one will be with the leakage. So I'm going for my simulation, and here is always the report minus something. So here you will find the HTML report, and you need just to find this HTML, this main document. Okay, and the same I will do for the case without the leakage, which is this one. Yeah, no leakage, simulation, no leakage. And you can add as many reports as you want, but for me 2 is enough. And now I will click on apply, and now this filter merge both reports together, and we will have nice report face to face to compare. Okay, so maybe I will open it in the web browser, so I can go here, and here is my merged report HTML, and nicely we can now follow the report. Okay, so comparison of the geometries. So we can see that here is the leakage, here is not the leakage, of course. The simulation, for example, what is nice to compare is the mesh cell size. So this radial impeller, for example, has just less than 700,000 cells, and with the leakage has more than 2.4. And well, the mesh inside the impeller is very the same. So you can see that the leakage simulation with the leakage costs a lot of cells to be added into your mesh, and any other parameters, okay, which is nice. And what would be nice to compare is, for example, the head. And as we can see, the report 1 is the one with the leakage. So we can see that the leakage takes more than 1 meter of the head. And if we go, for example, for the efficiency, so the efficiency is, for example, we can compare is more than 3%. So the leakage takes more than 3% of the efficiency from the simulation. So yeah, it is really nice. You can see the results and all the parameters at one place, face to face, and you can compare as many designs as you want. The same for torques. You can see that the graphs are intersect. Axial forces, of course, with the leakage there is lower axial force, total pressure difference, and so on and so on. And you can compare as you want and make some really expertise conclusion what to do and what will be, let's say, the next optimization for your design. Okay, and just to conclude, besides, okay, maybe I can show you some comparison of the automatical evaluation. So if we go at the bottom of, for example, some blade-to-blade view, okay, so you can compare also this blade-to-blade slices. Span 0.1 means it is at the 10% of the height between hub and shroud at the hub. So we can really see a detailed visualization of the flow along the blades, and so on and so on. And last but not least, you can really do your own visualization inside the ParaView. So for example, I have just made 2 perpendicular slices just to visualize the flow inside the leakage part. Yeah, so we can really nicely follow the geometry, also follow this blind or cavity-like domain, how the flow is how the flow is curved, and so on and so on. And yeah, really nice, and also cool picture for your presentation, of course. Okay, I think I can conclude with this nice visualization. So as you can see, you have all parameters what you need at one place. The setup and the simulation is pretty straightforward and easy to use, and you have really, I think the ParaView gives you, and graphical user interface together gives you a very powerful tool for nice visualization and now nice post-processing of your simulation and of your machines. Okay, so thank you, and I think it's time to go back to Luboš to conclude our webinar, I guess. So, okay, thank you. Luboš, are you ready? Can I? Okay, so I will stop sharing my screen and give it to Luboš. Okay.
Thank you, Radek, for your demonstration. It was impressive, and I think it's time to move in our webinar to the Q&A. So now it's time to answer your questions. So please ask your questions. You know that there are no stupid questions. There are only stupid answers, right? So feel free to put your questions, and we will have a look what we have here. So yeah, so I see the one question from Ankit Dave. How to control mesh parameters to capture leakage between stator and rotor? Okay, so Radek, would you answer this?
Yes, of course. So I will take the presentation back to me, which is this one. Yeah. Okay, hope you see my screen. Okay, and do you hear me? Yeah, I hope you hear me right. Okay, so I didn't forget to enable my microphone. Okay, so the setup of this part. Okay, very good question. So where is my correct? I think is this one. Right. So if I go to the components part, so first point how to manage the finest of the mesh inside the leakage is here. So from CFturbo we get I think 4 parts which is connected to the leakage. So wait, so this is not the leakage. All right. Where is it? Okay, I think here. Yes. So go to component 2, and yeah, here we have solid hub and solid shroud, and this casing shroud and casing hub are contours or surfaces at the leakage. So first one is to make really fine mesh finer mesh at this casing hub and shroud. So just increasing this number, we will get finer mesh at these parts. And because wall are merged together, so or type wall, if you change at one side, you will get the same number everywhere. So for example, if you would like to have really fine mesh, you can add it here together with the layers, of course. And and the more advanced tool how to enable that, and which is quite smart tool for advanced users. So if I enable this scripting, in which we can add a special treatment by the script, which I can show you directly. So inside this script, okay, I can define the level inside a gap. So it's not connected to the surface, but to the gap between two surfaces. So here I just define the names of the parts of the leakage. So basically it follows these names. For example, I had this RP and Q something, CO2 and solid hub, for example. So then I fill just this simple script. Where is it? Here. Okay, a little bit enlarge, right? And I will fill the level inside this gap. So this solid hub, let's say, and here will be inside the between the solid hub and any other surface. We will have the level 3 times higher than the background mesh. So it is nice and really powerful feature how to manage the mesh inside the leakage. Okay, I think.
Okay, thanks, Radek. Yeah, okay. Yeah, so Oliver, can you see any question you would like to answer?
Yes, I see one question from Rahul Shafekar. He is asking whether one can give in CFturbo balancing holes during the design of the impeller. Very often they are introduced into the hub. Right now we cannot do that in CFturbo, but because everything what we do in the meridional contour is done under the precondition of axisymmetry, and this whole feature would not fit into that concept. That's why we are planning to have an additional kind of post design step, which will be the very last one, and that will include this, for instance, this balancing hole feature. But this is not there right now.
Okay, thank you, Oliver. I can see 2 more questions on TCFD, so I will again ask Radek to answer them. The first one, is TCFD capable to simulate shut-off condition of pump?
Well, it is possible not really to simulate shutoff in sense of to preset 0 flow rate, but it is possible to simulate really low flow rate. Yeah. So if you set here, where is it? I hope you still see my screen, right? Okay. So in the setting of the boundary condition, so here basically if you go up to not 0, so with the 0 it doesn't work, but if you really set maybe something like this, or even less maybe, but not 0, it will work and it will simulate you the shutoff condition for the pump. Yeah, so basically it is possible.
Okay. Can you, Radek, also answer the question? Is there a check mesh on quality? The quality of the mesh check in TCFD?
Yes, I can answer, of course. There is, and it is hidden directly in the compare report. So maybe, okay, I will try to do this one, to use this one. So this is the mesh size, and if I open the details, we will see the mesh quality for for each component, and here are, for example, the skewness, what is important one, for example, the skewness, non-orthogonality, and other parameters, which is, I think, are familiar for all kinds of CFD meshes used for CFD simulation. Yeah, so it is included directly here. Yeah, and with some warnings, but it's just warnings, not errors. So there are really, because the only one mesh without a warning are those meshes with only cubes cells. So don't be afraid about these warnings, but you can really follow, and if you ask us, or we have somewhere the documents to this, which parameters are okay and their values. Yeah, so it is here in the report.
Okay, thanks. Another question. Hello, can you manually change turbulence model, K omega, K epsilon, and interface settings for frozen rotor or mixing plane? So Radek, would you answer also this?
Yes, I will. Okay, so back to the setting part. So first was the turbulence modeling, right? So the turbulence model are preset here, the basic one or the implicit one, but you can also use another one, just such as I have no clue now which particular one, but there are many others. So if you want to use some favorite which is not here, it can be scripted easily. And the second question was interface treatment, right? Okay, which is inside the component menus. So for the steady state simulation, we have two options. First one is the mixing plane approach. So which is of course, which is here. So mixing plane approach can be defined here at the interfaces. So now I am the component 2, and for example, if I would like to have the mixing plane between volute part and rotor part, I will set it here. For example, five let's say axial strips. So it will be done here, and now the mixing plane approach will be applied. And if there is a 0, then the frozen rotor or arbitrary mesh interface is applied. So it can be done here. And I don't know if it was the question, but you can also enable the transient simulation or steady state plus transient. In that case, for the transient, there is standard solid body motion, so always arbitrary mesh interface, and the mesh is really rotating. Yeah, so.
Okay, I think we have time. Yeah, I'm sorry. Okay, thank you, Radek. I think we have time for one last question. So, for example, this one: are you identifying surfaces in advance to calculate axial forces, and if so, how? So.
Okay, I can answer it because I have open it here. So inside the post processing, everything what is evaluated. what is evaluated for the torques and axial forces and so on are here in the torque patches menu. So in here you can really enable and disable what parts will be included into the axial and torque patches. So for example, as you can see, here are only the blades and rotating components, right? And for example, here hub and shroud are not checked for this evaluation, but can be checked very easily, and that's all. So here you can define it, and you can of course create more efficiencies, more reports with different setups, of course. Yeah.
Okay, thank you, Radek. So I think our time is over. So I will take the presentation back, and I think it's time to finish. So this is it from us. This is it from today's webinar. So it's time to really finish. So I would like to stress that you should feel free to contact us. I'm sure you know very well how to do that. The questions about CFturbo are about to be sent to CFturbo. The questions about TCFD are about to be sent to CFD support. We will gladly support you in your projects. It's our job and also a pleasure. So we are looking forward to get in touch with you. So anything more to say, Oliver?
I just want to say thank you for your time that you spent looking at our webinar. And if you have a CFturbo, the software installed, then please use that secondary flow path feature. And if there is anything you want to know or you run into troubles, so let me know and don't hesitate to ask us. Thank you very much, and bye-bye.
Okay, thanks. Radek, anything to say?
Yeah, I will just follow the Oliver's words. So thank you very much for watching us. And if you have any question connected to this case or any other case, just contact us at these emails and we will gladly answer you and support you in almost everything, right? Thank you very much, and bye.
All right then, so we leave you with that. So thank you for your attention. We are looking forward to collaborating with you. Stay tuned and bye bye for now.